Jai Bharat to all students. In last lecture we have started new topic trees in graph theory. Okay. In today's lecture we will discuss about more about trees and some its related theory which remaining in the last lecture. Okay. So first of all we will start with the tomorrow's lecture, basics of tree. Okay, revision of trees. Then we will I think mainly two theorems are remaining in this tree chapter. Okay, so we will complete in this topic. Okay, tree, this is a stick figure tree. Tree in graph theory look like this, and if it is a cycle then it's not a tree, it's only a graph. Also tree should be connected, okay, like this. This is disconnected graph. Okay, we all know what is disconnected and connected graph. Okay, so tree is a undirected connected, okay, undirected connected graph with no cycle. Okay, undirected means it has a not empty set of edge and vertex. Also it's keeps branching out like actual tree, but it's not required to draw it branching out from the bottom to top. Okay, like it's not always say like this bottom to top. Okay, it's maybe it's top to bottom like this also. Okay, this is also a tree. Okay, then tree has exactly one path between any pair of, okay, there is no multiple edges, or also if you connect any two vertex there is only exactly one edge path. Okay, if there is a x vertex and y vertex in which let's assume that 1 2 3 4 5 6 7 8 9 and 10 vertex are there. If you join x to y and if it is a tree then it should be a only one path. Okay, let's assume there is a two path, different path. Okay, from x to y one is red, from x to y one is blue path. Okay, now but here you can see that from this p vertex and q vertex you can see that there is a cycle is formed. Okay, but tree has a no cycle. Okay, so this is not possible, so our assumption is wrong. So this theorem holds the true. A tree has exactly one path between any pair of vertices. Okay, if you take this vertex and this vertex, okay, so there is should be always one path between any two vertex. Okay, if you let's say take this vertex, this vertex, this vertex and this vertex, if you draw a path in tree there should be only one path connecting them. Okay, then what is leaf and what is internal vertex? Okay, a degree of vertex of 1 is called leaf. Okay, that vertex is called leaf. Okay, degree of vertex means number of edges for that particular vertex. Okay, so this vertex is how many number of edges? 1 2 and 3. Okay, so this vertex has a 1 2 3 and 4. Okay, so this vertex has a degree of 4. So vertex of degree 1 is called leaf. Okay, and this tree has a total 8 leaves, green color. Okay, also bottom vertex is also called leaf, but in actual tree we will call as a bottom. Okay, not leaf. Okay, but in here graph only condition is degree of vertex should be 1, it's called leaves. Okay, sometimes degree of vertex 0 is also counted as a leaf, like this, only one vertex, isolated vertex. Okay, it's also called tree, it's also called as a leaves. If vertex with degree more than 2 or more than 2, it's called internal vertex. Okay, so this tree has a 4 internal vertex. Okay, leaves and internal vertex. Then theorem, every tree with at least 2 vertices have at least 2 leaves. Okay, so for this theorem to be true, we have make path between any two vertex. Pick any vertices x and make a path starting from the x. Okay, you can make path like this also. Okay, just we have to make path that we cannot go twice. Okay, if like this, then we cannot go from previous that path. Okay, if okay, so we have to make a path. Okay, so this with new vertex, and we have three edges. Okay, but one edges we have come with the x2 v2. Okay, so we have to make new edges. Okay, you can go like this. Okay, you have to make path with only one times. Okay, so till then there is no edge left. Okay, so this z is what is called leaf. Okay, so for that particular vertex z is leaf. Now start from z and make a different path. Okay, like this. Also we can get the new vertex, which is also a degree of vertex is a 1. Okay, so it's also a leaf. Okay, so we have now two leaves. Okay, from graph we can see that there is a number of leaves, but from theorem points of view we have to uh, solve like this from path to path. Okay, so it's a every tree with at least, if at least two vertices have at least two leaves. Okay, then this theorem is most IMP. All trees on n greater than is equal to 1 vertices have exactly n minus 1 edges. Okay, in last semester we have solved induction theorem. Okay, in that we have to find out if it is a hold for n is equal to 1 base step, and we have assumed that it is a true for n minus 1. If both steps are true, then we can say that this theorem is a true. Okay, let's say n is equal to 1 first of all. Okay, so there is only such a tree is a isolated vertex, only no edges. Okay, so 0 edges. So we have now n is equal to 1 vertex and 0 edges, so we can say that this n minus 1 edges is true. Okay, then next we have to find out that it's a true for 2 or more than 2. Okay, assume that theory holds for n minus 1 vertex. Okay, like this we have to assume that it is a true for the n minus 1 vertex. Okay, so now this is g graph, this is h graph. Okay, we remove one vertex and edges, okay, of g graph, that we make new subgraph. Okay, okay, so we have now remove v vertex leaf. Okay, so it's a edge is also removed. Okay, now h is also connected. Why? Because g is also connected. Okay, h has no cycle because g has also has no cycle. Okay, so now we have removed one vertex. So if this g has n vertex, so h will be n minus 1 vertices. Yes, but from first of all hypothesis, in induction hypothesis say that it's a true for n minus 1. This theory is true for n minus 1 vertex. Okay, so the n minus 1 vertex should be, so there is a n minus 2 edges. Edge is equal to n minus 2. Yes, this vertex, if vertex is n minus 1 and it is a true theory, then we can say that for this edge graph we have n minus 2 edges. Okay, now if we want to find out the edges of g graph, g tree. Okay, so we have removed only one edges. Okay, so for h graph edges is n minus 2, then we have to only add plus 1. Yes, we have removed one edges, then h subgraphs is become. Okay, so there is should be n minus 1 edges. So this theorem is both step are true. So we can say that this theorem is true. Okay, so all trees n or greater than or equal to 1 vertices have exactly n minus 1 edges. Then lemma theory, removing an edge from the cycle keeps connectivity. Okay, if we remove any edge, we can always make a path from y to x. Okay, it's not breakdown. Okay, then spanning tree, this is important. Okay, spanning tree is undirected graph, is a subgraph that's a tree and include all the vertices. Okay, we have to include all the vertices, only we have to remove cycle, we have to remove one edge from any cycle. Okay, and repeat until we arrive at a subgraph T with no cycle. Okay, we do not have to remove any vertex should be same. Okay, include all the vertex, but we have to remove one edges from cycle. Okay, it's called spanning tree. Then next is converse theory. Okay, what is converse theory? Okay, a reverse pattern. In last we have said that this n greater than or equal to 1 vertices have exactly n minus 1 edges. Okay, now reverse it, that if connected graph of n vertices has n minus 1 edges, then it's a tree. Okay, reverse. Okay, so we have to find out that this is a true or not. We already know this is true, but how, from mathematical formula, mathematical proof, we can prove that this statement is also true. Okay, let's assume G is a connected graph. It's not a tree. Let's assume the G is the connected graph on n vertices and has a n minus 1 edges. Okay, graph of n vertices has n minus 1 edges. Now let's say we already know that we can convert any graph into spanning tree. Okay, we have to remove edges. Okay, so it's a subgraph of G. Okay, so G contains a spanning tree. Let's assume this is a T. Yes, like this. G contains spanning tree of T. Okay, now we already know that spanning tree has a, what is, all vertices. Okay, so G and T has a same vertices. Yes, graph and spanning tree is the same vertices. Now, so if T is a spanning tree, then T has a n minus 1 edges. Yes, if it is a tree, then we can say that this has a n minus 1 edges. Okay, because T has a n vertices. Okay, which is a subset of the n minus 1 edges of G. So now we can say that G and T has the same edges. Yes, if T has n minus 1 edges and spanning tree is also a subset of graph G. Okay, so we can say that n minus 1 edges of G is the same edges. Okay, so if it is a n vertices and n minus 1 edges, we have same vertices, same edges, so we can say that G is equal to T. Yes, so G is a tree. Yes, from this proof we already know that from n vertices and n minus 1 edges, it's always become the tree. Okay, converse theory. Okay, next, forest. Okay, a forest is undirected graph with no cycle. Forest is the undirected graph with the no cycle. Okay, each connected component is a tree. Forest means there is more than 2 trees. Okay, we already know there is a hundred of thousands of tree that we call as a forest. Okay, so there are all the number of trees are there in the forest. Okay, so if each component is tree, but if we combine all the tree, then it will become forest. Like this, we have now, here we have now 2 trees and we have combined them, it's called forest. Okay, but it should be follow trees condition, there should be no cycle. Okay, and each connected component is a tree. This is also should be the tree and this should be also be a tree. Then all the tree combine and it's called forest. Okay, as a word say forest. Okay, in actual word forest mean there is a hundred or thousand of trees are in there. Okay, so in forest also there should be a more than 2 3 tree, then it's called forest. Okay, now let's say left tree, this how many vertices are there? 6. How many edges are there? We already know that it's n minus 1 edges, 5, and you can count also them 1 2 3 4 5. And right tree has a 4 vertices and 3 edges. Okay, if we for forest, if we total them, how many? 10 vertices and 8 edges. Okay, now a forest with n vertices and k tree. Forest with n vertices, total number of n vertices, and k number of tree has n minus k edges. Yes, why? Because for each tree, let's assume there is a 3 tree. Okay, now number of trees 3. So we have to how many if we calculate number of vertex and number of edges. Okay, so we have vertices n. Okay, so for edges we have to minus 1 from all the tree. Yes, if it is a 3 tree, we have to minus 3. Yes, each tree has a one less edges from vertex. Okay, so if there is a 3 number of tree, then we have to subtract 3 from the total number of vertex. Yes, so if there should be a k number of tree, there should be a n minus 1 k edges all the in the forest. Okay, forest, we have talk about forest. Okay, so let's assume that this 2 is a forest. Okay, so we have now 10 vertex. Okay, so now if we want to count edges, so there is a 2 tree, we have to just 10 minus 2, so is equal to 8. Yes, so this is the forest. Next is the rooted tree. Okay, this is the last topic, rooted. Okay, choose a vertex R and call it the root. Okay, we have to call it the root. Okay, so here R is equal to 5, given name. Okay, now for this rooted tree, root like in the actual tree we have root. Okay, main branch, then sub branch. Okay, like this. Okay, so follow all the edges in the direction away from the root. Okay, away from the root, like this. We have to make like this, all the edges in the direction away from the root. Okay, so for edges, let's assume for edges u set v, that vertex u is the parents of v. Okay, vertex u is the parents of v, like this. Okay, so and v is the child of u. Okay, like in root also. Okay, so the here phi is the parents of 4. Yes, why? Because arrow is like this. Yes, so first of all we have to make a vertex that is a root, then we can draw arrow like this. Yes, we have to choose any one root from any trees. Okay, then we can make the arrow and then we can find the parents and child. Okay, so 5 is the parents of 4 and 4 is the 5 is the parents of 4 and 4 is the child of 5. Yes, also here 5 is the also a parents of 6 and 6 is the child of 5. Yes, okay, so and children with the same parent, what which we will call is a sibling, brother and sister or brother. Okay, children with the same parents are called sibling. Okay, so now here 6 and 4 is the same parents, so we can say that 4 and 6 is a sibling. Yes, 4 and 6 is the parents child of 5, so we can say that 4 and 6 is the sibling. Okay, so here 5 is the parents of 4 and 6. Yes, 4 and 6 are children of 5. 4 and 6 are children of 5 and are sibling. 4 and 6 are sibling. Okay, now next make arrow like this. We have to make arrow away from the root. Okay, arrow's direction should be away from the root. Okay, like this. Okay, away from the root. Okay, so now 4 is the parents of 1 to 3. Yes, we can say that 4 is the parents of 1 to 3, and 1, 2 and 3 are children of 4 and are sibling to each other. Yes, 1 and 1, 2, 3 are sibling. Okay, and if you want to say that 8 and 7 are parents of 6. Yes, and 8 and 7 is sibling. Okay, now 9 and 10 is also sibling. Why? Because there is only one parents of 8. Okay, so this is a rooted tree. Okay, first of all we have to call any vertex as a root of that graph. Okay, then we have to make arrow or direction away from the root, and from that we have to tell that if it is a parents, children or sibling to each other. Okay, it's a called rooted tree. Okay, okay, so now this is your assignment question. Okay, so in that I already given the direction of arrow for this graph. This is a rooted tree. A is a rooted tree. C is a rooted tree, rooted vertex, and this is a also a C is a rooted vertex. Okay, so this is 3 is a rooted vertex. We from all the graph you have to find out the parents, children, and sibling of each vertex. Okay. Parents, children, and sibling of each vertex, all the 3 graph. Okay, I have already told you that which is a rooted vertex for this graph. C is a rooted vertex from this graph, A is a rooted vertex, and from this graph C is a rooted vertex. Okay, so this is your assignment question. Write it down and upload it in RNWIET application for attendance purpose. Okay, so now your lecture is completed.